66 million years ago, a profound silence enveloped the Late Cretaceous period, completely unaware of the celestial mechanics that were about to sever the timeline of life on our planet. We often think of extinction as a gradual biological failure, a slow fading of species unable to adapt to shifting climates or new predators. But the boundary separating the Mesozoic from the Cenozoic era was not written by biology. It was written by a singular, violent transfer of kinetic energy. In a fraction of a second, an object from the deep space intersected with the gravity well of our world, fundamentally altering the thermodynamics of the surface and the chemical composition of the atmosphere. This was a physical event that split the evolutionary history of the biosphere in two, proving that planetary ecosystems remain entirely at the mercy of orbital dynamics. When we observe this moment in the geological record, we are not just looking at the death of apex predators. We are looking at a cosmic vulnerability test, a stark reminder of the fragility of complex life that resonates with our modern understanding of planetary habitability and the cosmic silence we observe in the universe. If a biosphere that dominated for over 150 million years could be reset in an afternoon, the implications for the longevity of any civilization, including our own, are profound. Today we will explore the topic, the last day of the dinosaurs, Earth, before and after the end of the dinosaurs. Before we delve into the deep time of our planet, please take a moment to like this video, subscribe to the channel, and leave a comment below telling us exactly where in the world and at what time you are watching this documentary today. To understand the magnitude of what was destroyed, we must first reconstruct the architecture of the Late Cretaceous world. 66 million years ago, the surface of our planet bore little resemblance to the maps we rely on today. The supercontinent Pangaea had long since torn itself apart, driven by the relentless, churning convection of the mantle beneath the crust. The continents were in a state of deep fragmentation, drifting toward their modern positions but still profoundly alien in their configuration. The Atlantic Ocean was actively widening, unzipping the land masses, while North America was split entirely in two by a massive shallow body of water known as the Western Interior Seaway. Europe was not a continuous landmass, but an archipelago of islands scattered across a tropical sea, and the subcontinent of India was an isolated island drifting rapidly northward across the ancient Tethys Ocean. This deep tectonic fragmentation acted as an extraordinary evolutionary crucible. Isolated continents became planetary laboratories, forcing life to adapt within closed ecosystems and driving an explosion of biological diversity through divergent evolution. But the shifting architecture of the crust was merely the physical stage for a much larger thermodynamic engine. The Late Cretaceous was a textbook example of a greenhouse Earth. During this era, tectonic plates were moving at an accelerated rate. The rapid spreading of the seafloor at mid-ocean ridges meant the newly formed oceanic crust was hotter and more buoyant than it is today. This immense buoyancy displaced ocean water upward, pushing it onto the continental margins and resulting in global sea levels that were hundreds of feet higher than our current coastlines. Simultaneously, this intense global volcanic activity acted as a continuous planetary scale engine for carbon outgassing. Colossal volumes of carbon dioxide and methane were pumped directly into the atmosphere over millions of years. Today, climate scientists measure atmospheric carbon in parts per million, carefully monitoring minor fluctuations that threaten our modern stability. In the Late Cretaceous, carbon dioxide concentrations were exponentially higher, acting as a heavy thermal blanket that trapped incoming solar radiation with ruthless efficiency. The result was a world largely devoid of ice. There were no permanent frozen caps at the poles. Instead, lush, temperate rainforests and complex ecosystems extended all the way up to the Arctic Circle and across the landmass of Antarctica. This extreme thermal retention fundamentally altered the atmospheric and oceanic dynamics of the entire planet. The temperature gradient between the equator and the poles was surprisingly flat, without massive shelves of dense, freezing water sinking at the poles to drive robust deep ocean circulation. The Cretaceous oceans operated on a vastly different fluid dynamic model. The deep waters were often highly stratified and starved of oxygen, periodically resulting in oceanic anoxia events that wiped out bottom-dwelling marine life. Yet, on the sunlit surface, the warm, shallow seas were teeming with nutrients, fueling a hypersaturated marine food web. At a planetary scale, the implications of this climate state change entirely. When astrobiologists scan the cosmos for habitable exoplanets, the Late Cretaceous Earth represents a fascinating, extreme model of a stable, high-energy biosphere. It proves that a planet can sustain highly complex life even under severe greenhouse conditions, provided the transition to that state is gradual enough for the carbonate-silicate cycle to buffer the extremes. The Earth possessed a built-in geological thermostat that kept the oceans from boiling away, unlike the runaway greenhouse effect that ultimately sterilized our neighboring planet, Venus. The Cretaceous Earth managed to walk this thermodynamic tightrope for millions of years, maintaining a delicate, hothouse equilibrium. And it is precisely here that this geological reality begins to connect with a much larger question about the lifespan of civilizations. For tens of millions of years, the biological systems of Earth were perfectly calibrated to a warm, carbon-rich atmosphere. The biosphere was robust, operating at peak metabolic efficiency, thriving under a steady state of solar and geological energy. But this very stability masked a critical vulnerability. A highly specialized global ecosystem, mathematically optimized for a specific set of atmospheric parameters over deep time, is exceptionally fragile to sudden, unbuffered shocks. If this long-term environmental baseline is a prerequisite for complex life to evolve into intelligent civilizations, then the sheer fragility of such a highly tuned system becomes a potential barrier in the Fermi paradox. The Late Cretaceous Earth was a masterpiece of biological and climatic engineering, a world perfectly adapted to itself, but it was completely unprepared for the introduction of a new kinetic variable that originated entirely outside of its own atmospheric system. Within the lush environments of the Late Cretaceous, the terrestrial biosphere was undergoing a quiet but radical revolution in its energy processing infrastructure. For hundreds of millions of years, the land was dominated by gymnosperms such as ferns, cycads, and conifers. These plants relied on slow, energy-intensive reproductive cycles, often depending on the wind to distribute pollen across vast distances. But beneath the canopy of these ancient giants, a new biological technology had emerged and was rapidly conquering the planet. These were the Angiosperms, the flowering plants. Rather than relying on the random mechanics of the wind, Angiosperms co-opted the mobility of insects and other animals, creating a targeted, highly efficient delivery system for their genetic material. This shift in flora was not merely a change in the scenery, it represented a fundamental rewiring of the global carbon cycle. Flowering plants grow faster, reproduce quicker, and turn over their biomass at a vastly accelerated rate compared to conifers. The terrestrial energy grid was suddenly flooded with high-calorie, easily accessible fuel. This leads to a deeper consequence. The sudden influx of rapid growth vegetation forced an evolutionary arms race among herbivores. To exploit this new, fibrous food source, dinosaur lineages like the hadrosaurs and the ceratopsians evolved some of the most complex feeding mechanisms in the history of vertebrate life. They developed massive dental batteries, structures containing hundreds of tightly packed teeth that continuously replaced themselves. This allowed them to grind plant matter with industrial efficiency, extracting maximum caloric value before digestion even began. They became walking thermodynamic engines, processing immense volumes of vegetation and converting it into living biomass at unprecedented speeds, because the base of the terrestrial food web was processing solar energy so efficiently the ecosystem could support a top-heavy hierarchy of predators. Apex carnivores like the Tyrannosaurus rex were not biological anomalies. They were the inevitable result of an ecosystem that possessed an enormous surplus of available calories. The absolute mass of these predators, requiring monumental energy intakes just to sustain their basal metabolic rates, was directly subsidized by the accelerated metabolism of the forests and plains they hunted in. But the problem does not stop there. This extreme biological density was not confined to the land. The warm, shallow inland seas, fueled by rich nutrient runoff from the weathering continents, hosted their own hypersaturated food webs. Massive blooms of phytoplankton formed the foundation for entirely different phylogenetic trees, supporting vast schools of ammonites. In turn, these cephalopods sustained giant marine reptiles. the mosasaurs and plesiosaurs, which patrolled the coastal waters as apex aquatic predators. Meanwhile, the sky was a transitional battleground. Massive flying reptiles, the pterosaurs, were increasingly sharing the atmospheric niches with the rapidly diversifying avian dinosaurs, the direct ancestors of modern birds. At a planetary scale, the meaning of this changes completely. What we see in the Late Cretaceous is a biosphere operating at absolute peak capacity. Every conceivable ecological niche, from the deep soil to the upper canopy, from the shallow reefs to the open ocean, was occupied by highly specialized organisms. Evolutionary biologists refer to this as a saturated ecosystem. The species within this network were deeply interdependent, locked together in complex symbiotic relationships, predator-prey dynamics, and hyper-specialized feeding strategies. And right here, this hypothesis begins to connect with a larger question regarding the longevity of complex life in the universe. In systems theory, a network with a high degree of specialization and interconnection is incredibly robust against minor, localized disruptions. A localized drought or a gradual shift in regional temperature can be absorbed and buffered by the sheer diversity of the system. However, this same high connectivity makes the entire structure catastrophically vulnerable to a sudden systemic shock. When a species becomes perfectly adapted to a very specific set of environmental parameters, it loses its generalist flexibility. If this is true, it speaks not only to the past of the Earth, but to the future of any technological civilization. It suggests a deeply unsettling biological paradox. The natural end state of evolution in a perfectly stable environment is peak specialization, but peak specialization is exactly what strips a biosphere of its resilience against cosmic anomalies. As astrobiologists search for life on other planets, we must consider that mature, highly complex biospheres might inherently build themselves into a state of maximum fragility. The dinosaurs were not a failing dynasty entering a natural decline. They were the victims of their own ecological perfection, standing at the absolute pinnacle of an evolutionary house of cards, waiting for a disruption that would come not from the atmosphere, but from the silent void of deep space. Long before the sky over the Yucatan Peninsula ignited, the weapon that would reset the biological clock of our planet was forged in the deep freeze of the solar system. The exact origin of the Chicxulub impactor remains a subject of intense scrutiny in modern astrophysics, presenting a complex puzzle that forces us to look far beyond our own atmospheric boundaries. For decades, the dominant scientific consensus has pointed toward the main asteroid belt, a vast ring of primordial debris orbiting between Mars and Jupiter. However, competing hypotheses have recently emerged from orbital dynamics models, suggesting the object could have been a long-period comet originating from the Oort cloud, a dark, icy shell at the very edge of the solar system. According to this model, Jupiter's massive gravity could have kicked a comet into the inner solar system, where the tidal forces of the Sun tore it apart, sending a massive fragment on a collision course with Earth. Yet, when we examine the geological crime scene, the chemical signature strongly favors the asteroid belt. The global layer of debris left behind by the impact is heavily enriched with iridium, ruthenium, and other platinum group metals. This specific isotopic ratio is the hallmark of a carbonaceous chondrite. These are C-type asteroids, some of the darkest and most ancient objects in our solar system, essentially pristine time capsules holding the unaltered dust from the original solar nebula. They are rich in carbon, water, and volatile elements, making them incredibly dense and highly destructive physical projectiles. But the problem does not stop there. A carbonaceous chondrite floating in the main belt is harmless. To transform a dormant rock into a planet killer, it requires an engine of orbital disruption. Over millions of years, the asteroid was subjected to an incredibly subtle but relentless physical phenomenon known as the Yarkovsky effect. As the asteroid rotated in the vacuum of space, its surface absorbed solar radiation. The afternoon side of the rock then radiated that heat back into space as infrared photons. Because photons carry momentum, this thermal emission acted as a microscopic thruster, pushing against the asteroid. Over deep time, this imperceptible force of sunlight slowly altered the object's trajectory, pushing it into a gravitational resonance zone with Jupiter. At a planetary scale, the meaning of this changes completely. Jupiter acts as the gravitational conductor of the solar system. Once the asteroid drifted into an unstable resonance, the gas giant's immense gravitational tide violently warped its orbit, elongating it from a safe, circular path into an elliptical trajectory that crossed the orbit of Earth. This highlights a profound planetary paradox. Gas giants like Jupiter are often credited with shielding terrestrial planets by sweeping up rogue debris, but orbital mechanics prove they are also the primary engines of inter-system bombardment. The architecture of a solar system is inherently chaotic, and habitable zones are routinely intersected by high-mass projectiles. As the asteroid crossed into the inner solar system, it was not merely drifting toward a collision, it was actively being accelerated. As it intersected Earth's orbital path, the asteroid entered our planetary gravity well. Earth is not a static target in a cosmic shooting gallery. Its mass exerts a powerful pull, drawing the object in and steadily increasing its velocity. In the final hours before impact, the gravitational acceleration compounded the object's relative orbital speed. By the time it breached the outer exosphere, it was traveling at approximately 20 kilometers per second. This velocity is the most critical variable in the entire event. Kinetic energy scales with the square of velocity. Because the object was traveling at such extreme speeds, its physical mass, estimated to be at least 10 kilometers wide, was no longer the primary threat. The true weapon was the unfathomable reservoirs of kinetic energy it carried. And right here, this physical mechanism begins to connect with a much larger question regarding the survival of technological civilizations. When astrobiologists consider the Great Filter, a theoretical barrier that prevents life from advancing to an interstellar stage, the chaotic nature of orbital dynamics provides a sobering physical mechanism. If the Yarkovsky effect and the gravitational perturbations of gas giants constantly feed planet killers into the habitable zones of star systems, then long-term biological stability is a statistical anomaly. The dinosaurs did not do anything wrong. They did not mismanage their environment or exhaust their resources. They were simply erased by the blind, indifferent mathematics of orbital mechanics. If this dynamic is universal, it suggests that any civilization attempting to survive deep time must not only master its own planetary biosphere, but must eventually project its power outward to control the orbital trajectories of its entire solar system. The Chicxulub impact proves that a biosphere confined to a single planet and ignorant of its celestial neighborhood operates on a strictly limited, unpredictable cosmic timeline. As the massive rock and ice structure breached the outermost layer of the exosphere, the physical mechanics of the event defied standard aerodynamics. It did not burn up or fragment like a typical shooting star entering the atmosphere. Traveling at roughly 20 kilometers per second, the asteroid was moving significantly faster than the air molecules could physically move out of its path. Instead of passing through the air, the mass compressed the atmosphere directly in front of it, instantly superheating the gas into a blinding plasma shockwave. For a fraction of a second, a column of air stretching from the vacuum of space down to the surface of the Yucatan Peninsula was subjected to extreme hypercompression, creating a thermal corridor that temporarily erased the boundary between the planet and the void. But the true lethality of this event was governed by geometry. Modern supercomputer simulations mapping the structural deformation of the underlying bedrock have revealed that the object did not strike straight down. It approached from the northeast at an angle of approximately 60 degrees. In the physics of planetary impacts, a 60-degree trajectory is the absolute worst-case scenario. A shallower angle might have caused the object to skip or disperse its energy more broadly across the surface, while a perfectly vertical strike would have buried the majority of its kinetic energy deep into the mantle. The 60-degree angle was mathematically optimized to maximize the excavation of the crust, acting like a cosmic shovel that scooped the maximum possible volume of rock and launched it directly upward into the stratosphere. When the leading edge of the asteroid made contact with the shallow waters of the Gulf of Mexico, the physical laws of thermodynamics took absolute control. The object possessed an unfathomable reservoir of kinetic energy. Because energy cannot be destroyed, the sudden deceleration to zero velocity forced an instantaneous conversion of state. In less than 1 second, the kinetic energy of the asteroid was transformed into thermal energy and acoustic shockwaves. The sheer explosive yield is estimated to be equivalent to over 100 million megatons of trinitrotoluene. dwarfing the combined nuclear arsenals of human history by several orders of magnitude. At the precise point of contact, known as ground zero, the temperatures and pressures were so extreme that the normal structural integrity of solid matter ceased to exist. The asteroid itself, along with thousands of cubic kilometers of the Earth crust, did not shatter or break. It vaporized. The rock bypassed the liquid phase entirely, flashing directly into a superheated gas. The pressure pulse radiating outward from the impact zone forced the surrounding solid bedrock to behave like a liquid fluid. Through a mechanism known as acoustic fluidization, the extreme vibrational frequencies of the shockwave temporarily stripped the rock of its internal friction. The crust of the Earth rebounded exactly like a slow-motion droplet of water striking a pond. A central tower of molten rock surged miles into the air before collapsing back down upon itself, rippling outward to form a permanent circular mountain range within the crater, known today as a peak ring. Recent deep drilling expeditions into the Chicxulub peak ring have recovered core samples showing shattered granite originating from deep within the continental crust, brought to the surface in a matter of minutes. But the problem does not stop at the edge of the crater. This immense transfer of energy forces us to reevaluate the structural safety of any habitable world. At a planetary scale, the meaning of this physical interaction changes completely. We tend to view the crust of a terrestrial planet as a permanent, impenetrable shield protecting the biosphere. The mechanics of the Yucatan impact prove that under high-velocity kinetic stress, the crust acts merely as a thin, highly reactive membrane. And right here, this geological mechanism begins to connect with a larger question about the lifespan of technological civilizations. If the energy conversion of a single, localized impact can fluidize the crust and instantly reset the thermodynamic equilibrium of an entire planet, it highlights a profound vulnerability in the architecture of habitable worlds. When we look at the Fermi paradox and wonder why the galaxy is not visibly filled with communicative civilizations, we must consider the sheer kinetic violence inherent in orbital systems. The sudden conversion of kinetic energy to thermal energy is a universal physical constant. If a civilization fails to develop a planetary defense infrastructure capable of detecting and deflecting these high-mass projectiles, their extinction is not merely a possibility, it is a statistical certainty dictated by the mechanics of the cosmos. The crater buried beneath the Yucatan is not just a tomb for the dinosaurs, it is a geological warning sign regarding the mandatory requirements for long-term survival in a chaotic universe. While the mechanical violence of the impact excavated the physical crater, the true mechanism of global extinction was driven by the specific localized geochemistry of the impact site. The sheer kinetic energy of the asteroid could have scarred any part of the Earth, but the catastrophic atmospheric consequences were dictated entirely by the chemical composition of the Yucatan Peninsula. 66 million years ago, this region was a vast, shallow marine platform. The bedrock was primarily composed of two critical minerals laid down over millions of years of marine sedimentation. The first was calcium carbonate, essentially ancient limestone formed from the compressed shells of microscopic sea life. The second was anhydrite, a calcium sulfate mineral left behind by the evaporation of ancient seas. When the asteroid struck, the temperatures at ground zero exceeded 10,000 degrees Celsius, hotter than the surface of the sun. At this extreme thermal threshold, the bedrock did not merely melt, it underwent instantaneous chemical dissociation. The molecular bonds holding the rock together were violently ripped apart. The vaporization of the calcium carbonate instantly liberated hundreds of gigatons of carbon dioxide gas. Simultaneously, the vaporization of the anhydrite released an estimated 325 gigatons of sulfur, rapidly oxidizing into sulfur dioxide gas. This was not a slow, volcanic outgassing measured over millennia. It was an instantaneous planetary-scale injection of raw chemical compounds directly into the upper atmosphere. But the problem does not stop there. The simultaneous release of these two gases created a lethal, contradictory whiplash in the global climate system. Carbon dioxide is a long-term greenhouse gas designed to trap infrared radiation and gradually heat the planet. However, sulfur dioxide behaves entirely differently in the upper atmosphere. When exposed to water vapor in the stratosphere, sulfur dioxide rapidly converts into microscopic sulfate aerosols. These highly reflective particles form a dense planetary haze that acts as an aggressive mirror, reflecting incoming solar radiation back into deep space before it can reach the surface. The result is an immediate, catastrophic drop in global temperatures. The Earth was simultaneously loaded with the chemical triggers for both a long-term hothouse and a rapid deep freeze, setting the stage for a thermodynamic whiplash that biological organisms could not possibly adapt to. This leads to a deeper, more unsettling consequence heavily debated in modern paleoclimatology, often referred to as the unlucky location hypothesis. If the Earth had rotated for just 30 more minutes before the asteroid arrived, the impactor would have missed the Yucatan Peninsula entirely and plunged into the deep waters of the Pacific Ocean. The oceanic crust is primarily composed of basalt, a volcanic rock containing very little sulfur or carbonate. A deep ocean impact would have triggered devastating global tsunamis and massive vaporization of water, but it would not have injected the critical mass of sulfur aerosols required to plunge the planet into a deep, prolonged winter. Recent geological models suggest that only 1 to 13% of the Earth's surface possess the exact sedimentary mixture of carbonates and evaporates necessary to trigger a mass extinction of this scale. The dinosaurs were not just victims of an asteroid strike, they were the victims of a cosmic lottery, losing a game of planetary roulette dictated by the rotation of the Earth. At a planetary scale, the meaning of this changes completely. When astrobiologists analyze the potential habitability of exoplanets, they typically focus on the presence of liquid water, orbital distance, and atmospheric density. The Chicxulub event introduces a new, terrifying variable into the equation of cosmic survival: the localized geochemical distribution of the planetary crust. A biosphere could survive a massive kinetic impact if the crust at ground zero is chemically inert. The lethality of the universe is not just in the objects moving through it, but in the chemical interaction between those objects and the specific geology of the target. And right here, this geological mechanism begins to connect with a much larger question regarding the survival of technological civilizations and the Great Filter. We often assume that an advanced civilization could predict and survive natural disasters if they had enough time, but the chemical reality of the Yucatan impact demonstrates how rapidly a localized event can weaponize an entire atmosphere. If the survival of a complex biosphere depends on a 1 in 10 chance of an asteroid hitting the right type of rock, it suggests that the evolutionary paths on countless worlds may have been terminated simply due to bad rotational timing. For any intelligence looking out into the stars, the vaporization of the Earth crust serves as a stark reminder. A planet does not just nurture life. Under the right kinetic conditions, the very chemical foundation of the ground can instantly become the mechanism of its total destruction. In the fractions of a second following the vaporization of the Yucatan crust, the physical state of the impact zone transitioned entirely into a high-energy plasma. This was not an explosion in the conventional sense. A standard chemical explosion pushes air outward. This event was a hydrodynamic expansion of superheated rock and asteroid material operating at temperatures and pressures that defy terrestrial physics. The kinetic energy was so immense that the resulting plume of vaporized bedrock did not simply expand across the surface. It sought the path of least resistance. That path pointed directly straight up into the void of space. The sheer upward force of this expanding plasma bubble encountered the Earth atmosphere, but the air provided absolutely no resistance. The velocity of the expanding vapor was so extreme that it violently shoved the entire vertical column of the atmosphere, from the troposphere all the way up to the exosphere, entirely out of its way. It punched a temporary, localized vacuum tunnel straight through the protective envelope of our planet. The atmosphere was literally peeled back, exposing the molten surface directly to the vacuum of space. Scientists refer to this as a blowout phenomenon. For a brief window in time, the physical boundary between Earth and the cosmos ceased to exist. Through this atmospheric chimney, a colossal column of vaporized rock, molten glass, and pulverized asteroid fragments surged upward, entirely unhindered by air friction. Billions of tons of material were accelerated to suborbital velocities in a matter of seconds. Once this colossal plume breached the edge of space, expanding into the frictionless, freezing void, it began a rapid process of thermodynamic cooling. The vaporized continental crust quickly condensed in the microgravity environment of near space. It formed trillions of perfectly spherical droplets of liquid rock. These microscopic droplets, known to geologists as tektites, solidified into aerodynamic glass spherules as they radiated their intense heat away into the absolute cold of the cosmos. But the problem does not stop at the edge of the atmosphere. A significant fraction of this ejecta was accelerated beyond 11 kilometers per second, which is the exact mathematical threshold for the escape velocity of Earth. This leads to a deeper, more profound scientific consequence. By exceeding the gravitational tether of our planet, the Chicxulub impact ceased to be an isolated terrestrial event and became an interplanetary one. Millions of tons of Earth crust were permanently ejected from our planetary system, entering highly eccentric orbits around the Sun. And right here, this physical mechanism begins to connect with a much larger question regarding astrobiology and the potential distribution of life in the universe. Deep within the bedrock of the Yucatan Peninsula, primitive extremophile bacteria existed in the microscopic water-filled fractures of the stone. Laboratory simulations of hypervelocity, impacts, and extreme acceleration suggest that a small fraction of these deep biosphere microbes could theoretically survive the initial shock pressures, provided they were safely shielded deep within the core of larger solid boulders ejected into space. This theoretical mechanism of biological transfer is known as Lithopanspermia. At a planetary scale, the meaning of this event changes completely. The exact same mechanism that was systematically annihilating complex multicellular life on the surface of the Earth was simultaneously launching the deep microbial building blocks of the terrestrial biosphere into the void. Asteroid impacts are traditionally viewed by astronomers as the ultimate sterilization events. They are the great cosmic erasers, potential mechanisms for the great filter that eliminate developing ecosystems before they can achieve technological maturity. Yet, paradoxically, orbital mechanics dictate that they might also serve as the only natural engines capable of cross-pollinating a solar system. Over the past 66 million years, debris launched from this specific Tuesday in the Late Cretaceous has undoubtedly rained down on the sterile surface of the Moon, crashed into the rust-colored deserts of Mars, and perhaps even drifted into the gravitational pull of Jupiter to sink into the icy oceans of Europa. If humanity ever discovers microscopic, fossilized traces of terrestrial genetic material buried in the regolith of Mars, it will likely not be the result of deliberate human engineering. It will be the direct consequence of the kinetic violence of the Chicxulub impact. The sky above the dinosaurs did not just fall, it was inverted. For a brief, terrifying window, Earth ceased to be a closed biological system and bled its geology, and potentially its microbiology, out into the hostile expanse of the solar system. This forces us to fundamentally rethink the boundaries of habitable worlds. A planet is not an isolated island floating in the dark. It is an active participant in a violent, continuous cosmic exchange of physical material, where the line between a mass extinction event and a biological launch pad is separated only by the exit velocity of the debris. While millions of tons of pulverized Earth were permanently expelled into the solar system, the vast majority of the ejected material remained tethered by the gravitational pull of the planet. Trillions of droplets of molten rock and condensed vapor had been launched into suborbital space, spreading out over a ballistic canopy that enveloped the entire globe. But what goes up under the influence of gravity must inevitably return. Roughly 40 minutes after the initial impact in the Yucatan, this global cloud of debris began to fall back toward the surface. As these microscopic glass spherules re-entered the Earth atmosphere, they encountered the extreme friction of the mesosphere and the stratosphere. Each individual particle was minuscule, often no larger than a grain of sand, but they were traveling at orbital velocities, plunging into the gas envelope at thousands of miles per hour. The physical friction between this hypervelocity debris and the air molecules triggered a second, entirely different mechanism of planetary destruction. The kinetic energy of trillions of re-entering particles was simultaneously converted into intense thermal energy. The entire upper atmosphere of the Earth ignited into a glowing grid of incandescent plasma. The sky did not just change color, it became a contiguous planetary scale radiator. For a period lasting between several hours to a few days, the upper atmosphere reached temperatures exceeding 2,000 degrees Fahrenheit. Because heat in a vacuum, or near vacuum, transfers primarily through radiation, this superheated layer began bombarding the surface of the Earth with a relentless, invisible wave of infrared radiation. This was not a fire spreading across the ground. This was a thermal pulse delivered directly from the sky, operating precisely like the glowing element inside an industrial broiler oven. The geological evidence for this extreme thermal event is permanently etched into the rock record. When geologists analyze the Cretaceous-Paleogene boundary, the thin layer of sediment separating the age of dinosaurs from the age of mammals, they consistently find massive concentrations of elemental carbon in the form of soot and charcoal. For decades, the dominant scientific consensus interpreted this as proof of a global firestorm, a scenario where the infrared pulse spontaneously ignited every exposed forest and grassland on the planet simultaneously. But modern paleoclimatology has introduced a complex debate regarding the true limits of this model. Recent isotopic analyses of the soot suggest that while wildfires were indeed continent-spanning, they may not have been entirely global. The rotation of the Earth, the exact ballistic trajectory of the ejecta plume, and the unequal distribution of atmospheric moisture meant that some regions were subjected to lethal thermal radiation, while others were shielded by thick cloud cover or geographic positioning. This highlights the extreme difficulty of modeling fluid dynamics and thermodynamics on a planetary scale. But the problem does not stop there. The infrared pulse forces us to reevaluate the biological mechanisms of survival during a mass extinction. When the sky itself becomes a thermal weapon, biological adaptations like speed, strength, or armor become entirely irrelevant. You cannot outrun infrared radiation, which travels at the speed of light. Survival in those first few hours was dictated strictly by the physics of thermal shielding. Any creature standing exposed on the surface of the continent simply absorbed the radiation until its biological proteins denatured. The only way to survive the pulse was to place a physical barrier between the organism and the sky. Animals that could dive deep underwater, burrow into the soil, or hide within deep rock crevices were temporarily spared from the thermal radiation. This is exactly why the extinction was so highly selective. Small mammals, amphibians, and aquatic reptiles possess the physical dimensions and behavioral traits necessary to find immediate thermal refuge, while massive open-terrain dinosaurs had absolutely nowhere to hide. At a planetary scale, the meaning of this physical interaction changes completely. When we look at the architecture of terrestrial planets, we consider a thick, stable atmosphere to be the primary prerequisite for habitability. An atmosphere shields the surface from cosmic radiation, regulates global temperatures, and allows liquid water to pool. But the mechanics of the infrared pulse reveal a terrifying paradox in planetary physics. During a high-velocity kinetic impact, the atmosphere ceases to be a protective shield and is instantly weaponized. The friction of the re-entering debris turns the very gas envelope that sustains life into the instrument of its thermal eradication. If an asteroid of the exact same size were to strike a planet with no atmosphere, like our moon, the debris would simply fall back to the surface as cold dust. The thermal pulse is entirely a function of atmospheric density, and right here, this physical mechanism begins to connect with a much larger question regarding astrobiology and the search for extraterrestrial intelligence. If this dynamic is universally true, it means that the most hospitable planets in the galaxy, those with the thickest and most robust atmospheres, are also the most inherently vulnerable to thermal sterilization from kinetic impacts. It suggests that a life-sustaining atmosphere is a biological, double-edged sword. For any developing civilization, the sky is a protective blanket, right up until the moment it is struck, at which point it becomes a global incinerator. This mechanism adds a sobering variable to the Great Filter. It is not enough for a planet to remain geologically stable. It must remain kinetically undisturbed, because the very atmosphere required to nurture complex life is precisely what will amplify the lethality of a cosmic collision. While the atmosphere became a thermal weapon, the surface of the planet experienced a catastrophic failure of fluid dynamics. When the asteroid struck the shallow waters of the Gulf of Mexico, it did not merely create a splash. It excavated a transient cavity almost 30 kilometers deep into the continental crust. For a brief, unnatural moment, millions of cubic kilometers of ocean water were instantly vaporized or violently displaced outward, leaving a temporary gaping void in the sea. But physics abhors a vacuum. As the initial shockwave radiated outward, the surrounding ocean collapsed back into the superheated crater, colliding with the rebounding molten rock from the Earth crust. This chaotic intersection of collapsing fluid and rising magma generated an initial displacement wave estimated to be over 1 mile high. However, the true destructive power of a tsunami is not dictated by its initial height, but by the mechanics of wave propagation. In the deep ocean, a tsunami does not look like a towering wall of water. It manifests as a low, incredibly fast swelling of the sea surface, traveling at the speed of a commercial jet airliner. The wave retains almost all of its kinetic energy because there is very little friction with the deep ocean floor. But as this kinetic energy approaches the continental shelves, the fluid mechanics change abruptly. The shallowing seabed forces the wave to slow down, compressing its immense wavelength. Because the energy cannot simply disappear, it is forced upward. This process, known as shoaling, transformed the fast-moving ocean swells into towering, highly turbulent walls of water that struck the coastlines of North and South America with unimaginable force. But the problem does not stop at the immediate coastlines. The energy of the impact was so profound that it bypassed the ocean entirely and transmitted through the solid bedrock of the planet. Seismic waves traveling through the continental crust at speeds far exceeding the oceanic tsunami reached inland bodies of water thousands of miles away in a matter of minutes. This rapid ground oscillation triggered violent standing waves known as Seiches. Recent geological excavations at the Tanis fossil site in North Dakota have revealed perfectly preserved river ecosystems that were suddenly and violently buried by these seismic waves. The localized sloshing of inland rivers and lakes occurred long before the actual ocean tsunami could reach the coast, demonstrating that kinetic energy can weaponize distant, isolated bodies of water through direct seismic coupling. At a planetary scale, the meaning of this fluid dynamic disruption changes completely. The ocean is not just a body of water, it is the primary stabilizing heat sink and ecological reservoir of the Earth. As the megatsunami radiated outward, it did not merely wash over the land. Its sheer hydrodynamic force reached deep into the benthic zones of the ocean floor, violently scouring the seabed. Recent seismic imaging data collected deep beneath the modern Gulf of Mexico has revealed fossilized megaripples, massive underwater sand dunes standing 50 feet tall, permanently locked in the rock record. These ripples are the physical footprints of the retreating wave, proving that the ocean was churned from the surface all the way down to the abyssal plains. This total vertical mixing of the ocean column disrupted the marine stratification, bringing toxic, oxygen-starved waters from the deep directly to the sunlit surface. And right here, this geological mechanism begins to connect with a much larger question regarding the survival of technological civilizations. Throughout human history, the overwhelming majority of our infrastructure, economic hubs, and population centers have been clustered along coastlines, relying on the ocean for trade, agriculture, and climate stability. This coastal bias is a logical evolutionary step for any developing intelligence on a planet with liquid water. But the fluid mechanics of the Chicxulub impact reveal a hidden existential trap. Water is an incredibly efficient medium for transmitting kinetic energy over global distances. If a civilization builds its primary architecture along the shores of a global ocean, it is inherently wiring itself into a planetary-scale energy distribution network that can be instantly weaponized by a single kinetic impact. If this physical dynamic holds true across the universe, it suggests a profound vulnerability in the search for extraterrestrial intelligence. Astrobiologists often prioritize exoplanets with vast global oceans, viewing liquid water as the ultimate prerequisite for life. Yet, a water-dominated world possesses a built-in mechanism for global erasure. A kinetic impact on a dry planet creates a localized crater, but a kinetic impact in an ocean translates that localized energy into a global wave of destruction, effectively turning the planet's greatest asset into an instrument of systemic collapse. The sheer fluid violence that swept across the Late Cretaceous Earth stands as a stark physical reminder that proximity to the ocean is not just a biological advantage, it is a permanent existential gamble. As the immediate kinetic violence of the impact subsided, the ocean settled and the glowing sky began to cool. However, the true existential threat to the biosphere was only just beginning to assemble itself high above the clouds. The millions of tons of pulverized rock, soot from global wildfires, and vaporized minerals that had been blasted upward did not simply fall back to the ground. While the heavier ejecta had rained down during the infrared thermal pulse, an unimaginable volume of microscopic material remained permanently suspended in the upper atmosphere. The Earth had abruptly transitioned from a thermal crisis to an optical one. To understand the longevity of this new threat, we must examine the fluid dynamics of the Earth atmosphere. Our daily weather, including wind, rain, and cloud formation, is entirely confined to the lowest layer, known as the troposphere. When dust or smoke is injected into the troposphere, it is quickly washed out by the hydrological cycle in a matter of days or weeks. But the sheer explosive force of the Chicxulub impact punched straight through this turbulent weather layer, injecting billions of tons of ultrafine particulate matter directly into the stratosphere. The stratosphere is exceptionally stable, highly stratified, and entirely devoid of rain. Once microscopic particles reach this altitude, there is no natural mechanism to quickly wash them out. They become trapped, dispersed globally by high-altitude jet streams, forming a permanent, impenetrable planetary shroud. For decades, modern paleoclimatology has engaged in a complex debate regarding the exact composition of this atmospheric shield. Early models focused primarily on the soot generated by continent-spanning wildfires. Later, the focus shifted to the massive volumes of sulfur dioxide gas released from the vaporized Yucatan bedrock, which chemically reacted with stratospheric water vapor to form microscopic sulfuric acid aerosols. These aerosols are incredibly efficient at scattering incoming solar radiation. However, recent analyses of the sediment layers have introduced a third, highly potent variable. Geologists have discovered vast quantities of submicron silicate dust, essentially pulverized quartz from the continental crust, perfectly sized to remain buoyant in the stratosphere for up to 15 years. Modern supercomputer simulations suggest that it was not a single material, but the synergistic combination of soot, sulfur aerosols, and fine silicate dust that created an optical barrier of unprecedented efficiency. But the problem does not stop there. The formation of this stratospheric shield triggered a catastrophic failure in the fundamental energy economy of the planet. Life on Earth operates as a solar-powered engine. Every complex ecosystem relies entirely on the continuous transmission of photons from the sun to the surface, where plants convert that radiation into chemical energy. The aerosol layer did not merely dim the sun, it acted as a perfect planetary mirror, reflecting shortwave solar radiation back into deep space. Scientific models dictate that global light levels plummeted so severely that for an estimated period of 1 to 2 years, the surface of the Earth was plunged into a state of near total darkness. At high noon, the ambient light would have been comparable to a moonlit night. This leads to a deeper systemic consequence. Below a specific threshold of illumination, the biochemical machinery of photosynthesis simply ceases to function. The plants did not just stop growing, they began to starve, rapidly depleting their internal energy reserves before collapsing. The entire foundation of the global food web was abruptly severed from its sole energy source. At a planetary scale, the meaning of this atmospheric transformation changes completely. When we look up at a clear blue sky, we assume that atmospheric transparency is a permanent, guaranteed feature of a habitable world. But the chemistry of the impact winter proves that a life-sustaining atmosphere is remarkably fragile. The optical properties of an entire planet can be inverted from transparent to highly reflective in a matter of days, completely starving the surface of the electromagnetic radiation required to sustain complex biology. And right here, this atmospheric mechanism begins to connect with a much larger question regarding the Fermi paradox and the search for extraterrestrial intelligence. When astronomers use telescopes to search for biosignatures on distant exoplanets, they rely entirely on atmospheric spectroscopy, analyzing the light passing through the atmosphere of an alien world to detect oxygen or methane. But if a highly advanced, thriving biosphere can be instantly shrouded by an opaque layer of sulfur and silicate dust, that planet goes optically dark to the rest of the universe. If asteroid impacts are common in developing star systems, it suggests that the cosmos might be filled with habitable worlds trapped in prolonged periods of artificial darkness. A civilization trying to survive such an event would find themselves completely cut off from the energy of their host star, proving that the Great Filter might not just be a test of technological advancement, but a test of whether a species can survive the sudden, catastrophic loss of their own sun. As the stratospheric shield locked into place, completely severing the surface from the energy of the sun, the Earth experienced a brutal lesson in planetary thermodynamics. The sudden blockage of incoming solar radiation did not merely cause an optical blackout, it initiated a catastrophic thermal crash. The Late Cretaceous was an extreme hothouse world, completely devoid of polar ice, but within weeks of the impact, global temperatures plummeted. However, the physical rate of this cooling was not uniform across the globe. Because liquid water possesses a massive thermal inertia, the oceans retain their latent heat longer, cooling gradually over a period of months. The continental land masses, completely lacking this thermal battery, experienced a precipitous and immediate drop. Modern climate models suggest that surface temperatures on land may have plummeted by as much as 50 degrees Fahrenheit in a matter of weeks, plunging tropical and temperate ecosystems into a sudden, deep freeze for which they possessed absolutely no biological or evolutionary adaptations. But the problem does not stop at the freezing temperatures. While the surface was gripped by a rapidly accelerating impact winter, the atmosphere was churning into a highly reactive chemical cauldron. When the asteroid originally punched through the atmosphere, the hypercompressed plasma trail did more than just push air out of the way. The extreme heat of the entry column literally burned the atmosphere itself, forcing normally inert nitrogen gas to bond with atmospheric oxygen, synthesizing massive quantities of nitrogen oxides. Simultaneously, the vaporized anhydrite bedrock of the Yucatan Peninsula had injected hundreds of gigatons of raw sulfur dioxide directly into the stratosphere. This leads to a deeper, far more corrosive consequence. When these massive volumes of sulfur dioxide and nitrogen oxides combined with atmospheric water vapor, they initiated a planetary-scale chemical synthesis. The result was the vast formation of sulfuric acid and nitric acid within the cloud layers. When the hydrological cycle eventually began to push moisture back out of the sky, the precipitation that fell across the continents and oceans was not life-sustaining water. It was highly concentrated acid rain. The Earth was effectively subjected to a toxic chemical bath that lasted for years. Modern paleoclimatology features intense debate regarding the exact global severity of this acidic deluge. Some models argue that the acid rain was highly localized to the hemisphere of the impact, while others suggest the high-altitude winds distributed the toxic precipitation worldwide. Regardless of the geographic spread, the ecological devastation extended far beyond the immediate burning of surviving plant tissue. In terrestrial ecosystems, the acid soaked deeply into the topsoil, stripping away vital chemical nutrients and mobilizing toxic heavy metals like aluminum. This silent chemical poisoning destroyed the root systems of the dormant seeds that were desperately waiting out the darkness, neutralizing the biological backup systems of the forest. However, the most catastrophic chemical damage occurred in the upper layers of the global ocean. The surface waters absorbed millions of tons of these acidic compounds, triggering a sudden, severe drop in marine. This rapid ocean acidification was an absolute death sentence for any marine organism that relied on calcium carbonate to build its shell or structural skeleton. Microscopic calcareous phytoplankton, the foundational pillar of the marine food web, literally began to dissolve alive in the ocean. At a planetary scale, the meaning of this chemical transformation changes completely. We fundamentally view the water cycle as the ultimate mechanism of biological preservation on a habitable world. Water is the universal solvent that nurtures complex life. But the geochemistry of the Chicxulub aftermath proves that the hydrological cycle can be effortlessly weaponized. Under the right kinetic conditions, the very rain that a biosphere relies on for survival can be chemically inverted into an instrument of mass corrosion. The ocean, typically a stabilizing force for life, becomes a chemical trap when its buffering capacity is overwhelmed by atmospheric fallout. And right here, this geochemical mechanism begins to connect with a much larger question regarding planetary habitability and the Great Filter. When astrobiologists define the habitable zone around a distant star, They strictly define it as the exact orbital distance where liquid water can exist on the surface. But the reality of this impact demonstrates that the mere presence of liquid water is not enough to guarantee long-term biological survival. The chemical stability of that water is incredibly fragile. If an advanced civilization on an exoplanet is struck by a kinetic object, their perfect proximity to their host star will not save them when their entire planetary water cycle turns highly acidic. The extinction of the dinosaurs proves that the boundaries of life are not just dictated by temperature and light, but by a delicate, easily shattered chemical equilibrium. The cosmic Goldilocks zone is an illusion if the planetary chemistry can be so rapidly inverted, proving that even the most perfect oceans can be turned into a corrosive wasteland by a single falling rock, while the terrestrial ecosystems were being battered by freezing temperatures and toxic soils. The most rapid and absolute biological collapse was unfolding beneath the waves. The global ocean is often viewed as the ultimate ecological buffer, a vast thermal and chemical sink that protects marine life from surface volatility. But the biological architecture of the ocean contains a fatal design flaw. Unlike terrestrial forest, which can store massive reserves of energy in roots, trunks, and dormant seeds, the marine food web operates entirely on a real-time energy feed. The absolute foundation of this ecosystem is phytoplankton, microscopic organisms suspended in the upper sunlit layer known as the photic zone. Phytoplankton do not have the capacity to store long-term energy or go into deep dormancy. Their entire life cycle is measured in a matter of days, completely dependent on the continuous, uninterrupted transmission of photons from the sun. When the stratospheric shield of soot and sulfate aerosols plunged the Earth into prolonged darkness, the marine biological engine did not gradually slow down. It seized almost instantly. Deprived of solar radiation, the phytoplanktons simply stopped photosynthesizing and died. This was compounded by the rapid ocean acidification caused by the atmospheric sulfur fallout, which actively dissolved the delicate calcium carbonate shells of specific plankton groups such as the calcareous nanoplankton. The fossil record captured in deep-sea sediment cores perfectly illustrates this catastrophic failure. Geologists identify the exact boundary of the impact by a sudden, stark disappearance of complex microscopic shells, replaced by a layer of dead, barren clay. This leads to a deeper consequence dictated by the unforgiving mathematics of trophic levels. In any ecosystem, energy moves upward from producers to consumers, losing roughly 90% of its volume at each transfer step. Because the marine food web was cut off at its absolute base, the starvation cascaded upward with terrifying speed. Zooplankton, which feed on phytoplankton, were eradicated in weeks. This immediately triggered the systemic collapse of the next trophic tier, most notably the ammonites. These shelled cephalopods were incredibly abundant and diverse, filling the oceans of the Late Cretaceous, much like schools of fish do today. But ammonites possessed a critical biological vulnerability. They lived in the upper water column and produced thousands of tiny planktonic larvae that drifted near the surface, relying entirely on the vanishing microscopic life for food. As the surface starved, the entire reproductive future of the ammonite lineage was erased in a single generation. Interestingly, modern paleontology reveals a stark contrast when comparing the doomed ammonites to their distant relatives, the nautiluses, which successfully survived the extinction. The nautiluses inhabited the deeper, darker zones of the ocean far below the photic zone. Furthermore, they produced a small number of large, heavily provisioned eggs that developed slowly on the deep sea floor, bypassing the starving surface waters entirely. Their slower metabolism and deep water isolation provided just enough of a biological buffer to ride out the cosmic winter. This proves that survival during a mass extinction is rarely about strength or dominance. It is entirely dictated by metabolic requirements and a reproductive strategy. But for the apex predators of the Cretaceous oceans, there was no deep water refuge and no way to slow their metabolism. The sudden eradication of ammonites and small marine reptiles severed the caloric pipeline required to sustain the massive mosasaurs and plesiosaurs. These giant marine reptiles were the pinnacle of evolutionary design, perfectly adapted for speed and power, but their immense physical size demanded a continuous, massive intake of calories. You cannot hibernate a 50-foot marine predator. As their prey vanished, these apex hunters rapidly starved, their lineages completely extinguished from the fossil record in a geological blink of an eye. The only marine ecosystems that temporarily thrived during this period were the benthic zones, the deep abyssal plains at the bottom of the ocean. For a brief window, detritivores and deep-sea scavengers feasted on the unprecedented global rain of dead organic matter sinking from the dying surface above. At a planetary scale, the meaning of this systemic collapse changes completely. The eradication of the sunlit marine biosphere reveals a fundamental paradox regarding the fragility of habitable worlds. Ecosystems that operate directly on stellar energy are the most vibrant, diverse, and biologically complex systems in nature, yet they are mathematically the most vulnerable to sudden erasure. And exactly here, this biological mechanism connects with a profound question in astrobiology and the search for extraterrestrial intelligence. When we look to the stars, we naturally prioritize finding Earth like planets with surface oceans, assuming they are the best candidates for long-term biological stability. But the collapse of the Cretaceous food web suggests that surface biospheres are inherently fragile, permanently exposed to the kinetic violence of their star systems. If we want to find truly resilient life in the universe, life capable of surviving the great filter of asteroid impacts and orbital chaos, we might need to look away from sunlit surface oceans entirely. Subsurface ocean worlds, like the icy moons of Europa or Enceladus, rely on internal geological heat and chemosynthesis rather than photosynthesis. A kinetic impact that darkens the sky of a surface world would be entirely unnoticed by an ecosystem thriving in the pitch-black abyss of an ice moon. The sudden death of the Earth oceans forces us to reconsider the cosmic architecture of life. The most enduring biospheres in the galaxy may not be the ones bathing in the light of their stars, but the ones hiding in the absolute dark, insulated from the violent mechanics of the cosmos by miles of impenetrable ice. While the sudden optical blackout dissolved the foundation of the marine ecosystems in a matter of weeks, the biological collapse on the continents followed a slightly different, yet equally ruthless, mechanical timeline. The terrestrial food web was fundamentally anchored by photosynthesis. But unlike the microscopic plankton of the oceans, terrestrial plants possess deep biological reservoirs. Roots, tubers, and dormant seeds buried beneath the toxic topsoil did not immediately die when the sun disappeared. Instead, they entered a state of suspended animation, locking away their stored chemical energy. However, this underground energy bank was entirely inaccessible to the massive herbivores that dominated the Late Cretaceous landscapes. Organisms like the heavily armored ceratopsians and the immense hadrosaurs were engineered for a hyperproductive greenhouse world. Their colossal physical frames demanded a constant, massive throughput of fresh vegetation simply to maintain their basal metabolic rates. When the atmospheric aerosol shield blocked the solar radiation, the forests ceased generating new edible biomass. The herbivores suddenly faced an insurmountable thermodynamic deficit. The immense size that had once protected them from predators now became an absolute death sentence. As the primary consumers starved in the freezing darkness, the trophic energy pipeline to the apex predators was abruptly severed. Carnivores like the Tyrannosaurus rex, requiring vast quantities of meat to sustain their endothermic metabolisms, quickly exhausted the rapidly decaying biological capital of the dying world. The extinction on land was not a theatrical battle for survival. It was a quiet mathematical certainty, dictated by the physics of caloric intake versus energy expenditure. But the problem does not stop there. The fossil record clearly shows the sudden erasure of these massive lineages at the geological boundary, but modern paleontology has unearthed a complex chemical timeline suggesting the asteroid might not have acted entirely alone. This leads to a deeper scientific debate, forcing us to look away from the sky and down into the internal thermodynamic engine of the Earth itself. Half a world away from the catastrophic impact in the Yucatan, the Indian subcontinent was actively tearing itself apart. This was not a localized volcanic eruption. It was a massive flood basalt province known to geologists as the Deccan Traps. For hundreds of thousands of years prior to the asteroid strike, colossal fissures in the Earth crust were vomiting millions of cubic kilometers of molten rock onto the surface. This prolonged geological rupture acted as a planetary-scale outgassing valve, pumping unfathomable volumes of carbon dioxide and sulfur dioxide directly into the atmosphere. This reality forms the core of a highly debated scientific model known as the press-pulse hypothesis. According to this model, the press was the chronic, long-term environmental stress inflicted by the Deccan traps. The continuous injections of volcanic gases had already triggered violent swings between extreme greenhouse warming and highly toxic acid rain, slowly degrading the resilience of the global biosphere. The ecosystems of the Late Cretaceous were already highly stressed, pushed to the absolute brink of systemic failure. The asteroid was simply the pulse, the sudden extreme kinetic blow that shattered an already compromised biological architecture. And right here, this geological theory begins to connect with a much larger question regarding planetary mechanics and seismic physics. Recent high-precision uranium lead dating of the crystalline structures within the Deccan basalt layers has revealed a terrifying chronological synchronization. The most violent, high-volume phase of the Indian volcanic outgassing appears to perfectly align with the exact timeline of the Chicxulub impact. Geophysicists now propose a chilling physical mechanism to explain this coincidence, known as seismic coupling. The kinetic energy delivered by the asteroid impact was so immense that it transmitted a global magnitude 11 seismic shockwave deep through the mantle of the Earth. Because the Earth is a highly conductive, spherical acoustic medium, these immense seismic waves radiated outward and naturally converged on the exact opposite side of the planet, a phenomenon known as antipodal focusing. When these waves slammed into the subsurface magma chambers of the Deccan traps, they violently agitated the molten rock, fracturing the surrounding crust and hyper-accelerating the volcanic eruptions. The Earth was not merely struck by a rock from space. The planet was violently squeezed, causing it to structurally hemorrhage from its opposite hemisphere. At a planetary scale, the meaning of this changes completely. We tend to view cosmic hazards and internal geological hazards as separate, independent threats to habitability. But the seismic resonance between Chicxulub and the Deccan traps proves that an external kinetic strike can instantly weaponize the internal geology of a world. If this physical mechanism holds true, it fundamentally alters our understanding of planetary survival and the Great Filter. A technological civilization on a distant exoplanet might successfully map the orbits of dangerous asteroids, but they must also calculate the acoustic fragility of their own planet. An impact that might otherwise be survivable becomes an absolute extinction event if the kinetic energy triggers a synchronized planetary-scale volcanic rupture. The longevity of any advanced biosphere depends not only on avoiding the debris of the solar system, but on surviving the internal acoustic resonance of the very ground it stands on. The fossil record from this exact geological boundary presents a ruthless physiological filter. When the dust finally began to settle, the biosphere had been radically pruned, but the selection process was not random. On land, virtually no animal weighing more than 25 kilograms survived the impact winter. This was not a coincidence, it was a strict mathematical limit imposed by basal metabolic rates. An animal is essentially a biological engine, and physical size dictates the absolute idle speed of that engine. A massive theropod dinosaur could not simply choose to eat less. Its cellular infrastructure demanded thousands of calories a day just to maintain its internal body temperature and basic organ function. When the global food web collapsed, these massive biological engines rapidly burned through their own fat reserves and starved. Absolute physical size, which was the ultimate evolutionary advantage during the stable Cretaceous period, instantly became a fatal liability in a post-impact world. But the problem does not stop at physical dimensions. The extinction event aggressively tested the thermodynamic strategies of life itself. We see a stark divergence in the survival rates of warm-blooded versus cold-blooded animals. Ectotherms, such as crocodiles, turtles, and snakes, experience surprisingly high survival rates. Because they do not expend massive amounts of internal energy to heat their own bodies, their baseline caloric requirement is a mere fraction of a similarly sized mammal or bird. A crocodile can lower its heart rate to a few beats per minute and survive for over a year without consuming a single meal. Furthermore, many of these reptiles inhabited freshwater river ecosystems. Unlike the oceans, which relied on live phytoplankton, these freshwater webs were heavily supported by dead organic matter washing in from the land, providing a slow-burning, detritus-based food source that did not immediately collapse when the sun disappeared. This leads to a deeper physiological paradox. If low metabolism was the absolute key to survival, how did the early mammals and the ancestors of modern birds survive? Both groups were highly active endotherms, burning massive amounts of energy to stay warm in the freezing darkness. The answer lies in a specialized metabolic emergency brake known as torpor. Early mammals were generally small, nocturnal, and capable of burrowing deep underground, completely insulating themselves from the initial infrared thermal pulse and the subsequent freezing winter. More importantly, many possess the ability to enter states of deep hibernation, drastically lowering their body temperature and metabolic rate until environmental conditions improved. They essentially fast-forwarded through the worst phases of the impact winter while safely locked in a low-energy state beneath the toxic soil. Above ground, the surviving avian dinosaurs relied on a completely different economic advantage. The fossil record indicates that the birds that survived the boundary were primarily terrestrial granivores, meaning their diet consisted heavily of seeds. While the adult forests were burned, frozen, or starved of light, the topsoil was packed with millions of dormant seeds. A seed is a biological time capsule, a heavily armored package of dense chemical energy designed to withstand extreme environmental stress. While the leaf-eating herbivores starved waiting for new growth, the seed-eaters simply walked across the decaying landscape, harvesting the stored biological batteries left behind by the dying forests. In this inverted ecosystem, the apex hunters perished, and the biological scavengers inherited the Earth. At a planetary scale, the meaning of this survival mechanism changes completely. We often misinterpret the concept of survival of the fittest to mean the survival of the strongest, the fastest, or the most dominant. The Chicxulub impact proves that during a global kinetic catastrophe, fitness is entirely redefined as metabolic flexibility and environmental minimalism. The organisms that dominated the planet were effortlessly erased, while the marginalized low-energy generalists hiding in the mud and the dark were spared. And right here, this physiological reality begins to connect with a much larger question regarding the longevity of civilizations and the Great Filter. When we imagine advanced extraterrestrial intelligence, we often envision hyper-complex, high-energy civilizations that engineer their entire star systems to feed their growing demands. But the biological history of our own planet issues a stark warning. High energy requirements create a fragile architecture. If an advanced civilization requires the continuous uninterrupted output of massive energy grids just to survive their baseline existence, they are functionally identical to a Tyrannosaurus rex. A sudden cosmic shock, a stellar flare, or a kinetic impact could sever their energy supply, leading to rapid systemic collapse. The surviving organisms of the Cretaceous-Paleogene boundary suggest that the true key to long-term survival in a chaotic universe is not the ability to consume maximum energy, but the ability to safely power down, hide in the dark, and patiently outlast the catastrophe. How do we know all of this actually happened? For a long time, the sudden disappearance of the dinosaurs was attributed to a gradual biological decline, a slow fading of species unable to adapt to shifting environments. But the absolute truth of their demise was eventually found locked inside a layer of clay no thicker than a human finger, scattered across the entire globe. This thin band of rock represents the Cretaceous-Paleogene boundary, and it contains a chemical signature that simply does not belong on the surface of the Earth. When scientists analyzed this global clay layer, they discovered staggering concentrations of iridium. Iridium is a heavy platinum group metal that is exceptionally rare in the Earth crust. During the early molten formation of our planet, dense elements like iron and iridium sank deep into the core due to gravity, leaving the rocky exterior highly depleted. However, iridium is incredibly abundant in carbonaceous chondrite asteroids. Finding a uniform, worldwide dusting of this specific element proved that a massive extraterrestrial body had not just struck the Earth, but had completely pulverized itself and settled over the entire biosphere. The asteroid did not just hit the planet, it became part of the planet. But the problem does not stop at chemical anomalies. To permanently silence the debate between a cosmic impact and terrestrial volcanic activity, Geologists had to look at the physical deformation of the bedrock itself. Within the boundary clay, they found shocked quartz. Quartz is one of the hardest and most common minerals on Earth, but inside this specific layer, its microscopic crystal lattice is shattered in a highly predictable pattern of intersecting parallel lines. Volcanic eruptions, no matter how violent, build pressure slowly from below. They melt and push rock. Shocked quartz, however, requires a sudden, extreme pulse of kinetic energy, an instantaneous hypervelocity shockwave that forces the crystal to structurally deform before it even has time to melt. On Earth, this specific microscopic damage is only generated by two events: nuclear detonations and asteroid impacts. This leads to a deeper consequence regarding how we interpret deep time. The fossil record is notoriously blurry. A single inch of limestone can represent 10,000 years of slow accumulation, making it nearly impossible to pinpoint the exact day a species died. The extinction initially looked gradual simply because of the low resolution of the geological tape recorder. But recent excavations at a site called Tanis in North Dakota have provided an unprecedented, terrifying level of clarity. Tanis is not a standard fossil bed. It is a mass grave created by the immediate seismic sloshing of an inland river, burying an entire aquatic ecosystem alive in a matter of minutes. The preservation is so immaculate that paleontologists have found freshwater sturgeon with microscopic glass tektites trapped directly inside their gills. These fish literally choked on the molten debris raining down from the Yucatan impact thousands of miles away before the seismic wave entombed them in mud. Even more astonishing, by analyzing the seasonal growth rings in the bones of these fossilized fish, scientists have determined exactly when the asteroid struck. The outer layer of bone was just beginning its rapid growth phase, proving that the sky fell during the spring in the northern hemisphere. The plants were budding, and animal life was emerging from winter dormancy, striking the ecosystem at its most vulnerable state of energy expenditure. At a planetary scale, the meaning of this geological preservation changes completely. We tend to think of history in terms of architecture and monuments, assuming that grand events leave behind massive, highly visible ruins. But the Cretaceous-Paleogene boundary demonstrates the ultimate erasing power of a planetary biosphere. Within a few million years, continents shift, mountains erode, and oceans consume the land. The only permanent record of the most violent day in the history of complex life is a microscopic chemical dusting and a few shattered crystals buried in the mud. And right here, this geological reality begins to connect with a much larger question regarding the Fermi paradox and the search for extraterrestrial intelligence. If we are searching the galaxy for evidence of ancient, destroyed civilizations, we must fundamentally adjust our expectations. The Great Filter does not leave behind crumbling skyscrapers, rusted machines, or planetary monuments. The relentless tectonics and weather systems of any habitable planet will grind advanced infrastructure into dust over geological timescales. If an alien civilization was wiped out by a kinetic impact, or even a self-inflicted nuclear winter, their final legacy would look exactly like the layer of clay left by the dinosaurs. We will not find them through optical telescopes looking for dead cities. We will only find them by landing on their planets, digging deep into the bedrock, and searching for the silent, microscopic isotopic anomalies that mark the exact moment their world came to an end. The darkness could not last forever. Eventually, gravity and the hydrological cycle began to overwhelm the atmospheric suspension. Over several years, the sulfuric acid rained out, and the silicate dust settled back to the surface. As the first unobstructed photons of solar radiation finally struck the continents, they illuminated an alien, devastated landscape. The dense, multi-layered forests of the Cretaceous were gone, replaced by a global expanse of ash and decaying organic matter. But nature abhors a vacuum. The fossil record shows an immediate, explosive global phenomenon known as the fern spike. Fern spores are incredibly robust, capable of surviving extreme thermal and chemical stress. They rapidly colonize the sterile, nutrient-poor ash, acting as the ultimate pioneer species, anchoring the toxic topsoil and beginning the arduous process of rebuilding the terrestrial biosphere. But the problem did not stop with the return of sunlight. the atmosphere was still profoundly out of balance. The vaporization of the Yucatan bedrock and the prolonged eruptions of the Deccan traps had loaded the sky with thousands of gigatons of carbon dioxide. With the stratospheric mirror gone, the planet was instantly subjected to a massive greenhouse effect, transitioning violently from a deep freeze into an extreme thermal spike. To survive, the Earth had to engage its ultimate deep-time planetary thermostat, a geochemical process known as silicate weathering. As acidic rain fell on exposed silicate rocks, a slow, relentless chemical reaction occurred, binding the atmospheric carbon into liquid bicarbonates that washed into the ocean, eventually precipitating out as new limestone on the sea floor. This mechanism is incredibly slow, operating on a time scale of hundreds of thousands of years, but it is the absolute physical prerequisite for long-term planetary habitability. If this carbon drawdown mechanism did not exist, Earth would have suffered a runaway greenhouse effect and permanently transitioned into a sterile pressure cooker like Venus. As the climate gradually stabilized, the surviving biosphere found itself in a profoundly altered ecological landscape. For 150 million years, the dinosaurs had occupied every large-scale niche on the planet, suppressing the evolution of other terrestrial vertebrates. Their sudden absence triggered one of the most violent biological reorganizations in Earth history, a mechanism biologists call adaptive radiation. The surviving mammals, previously restricted to small, nocturnal, burrowing forms by the predatory pressure of the dinosaurs, were suddenly granted total ecological release. Without massive herbivores consuming the recovering vegetation, and without giant carnivores hunting them, mammalian bodies experienced rapid, extreme morphological changes. Within a few million years, an evolutionary blink of an eye, these small generalists radiated into a staggering variety of specialized forms, scaling up in physical size by orders of magnitude to become the new apex predators and megaherbivores of the Cenozoic era. This leads to a deeper consequence regarding the evolution of intelligence. The mammalian biological architecture, forced into existence by the oppressive shadow of the dinosaurs, possessed unique traits that would redefine the trajectory of life. Mammals had evolved endothermy to survive cold nights, complex inner ear bones for acute hearing in the dark, and most importantly, an expanded neocortex to process complex sensory data. When the asteroid cleared the board, it did not just change the size of the animals, it fundamentally shifted the evolutionary focus from physical dominance to neurological complexity. The biological hardware required for advanced intelligence was suddenly unleashed from its subterranean confinement. At a planetary scale, the meaning of this biological reset changes completely. We tend to view mass extinctions as the ultimate tragedies, cosmic errors that temporarily break the chain of life. But the adaptive radiation of mammals suggests a profound, terrifying paradox regarding the Fermi paradox and the emergence of technological civilizations. A biosphere operating in perfect, uninterrupted stability eventually reaches an evolutionary dead end. The dinosaurs were so perfectly adapted to their environment that they had no biological incentive to develop higher-order intelligence or technology. If the asteroid had missed the Earth by a fraction of a degree, the reptilian monopoly would have likely continued indefinitely, and the mammalian lineage would have remained permanently trapped in the undergrowth. If this mechanism is a universal constant, it means that the Great Filter is not just a destroyer of worlds, it is a mandatory biological catalyst. The emergence of a spacefaring, technological civilization might actually require a catastrophic kinetic intervention to shatter the stagnation of peak biological specialization. As we look back at the last day of the dinosaurs, we are forced to confront an unsettling truth about our own existence. Humanity is not the pinnacle of a smooth, continuous evolutionary ladder. We are the direct, chaotic descendants of a cosmic accident. Every piece of human technology, every city we have built, and every signal we send into the stars is built on the foundation of a shattered world. We exist only because a carbonaceous rock from deep space intersected with a specific chemical deposit on a specific Tuesday, proving that the violent mechanics of the cosmos do not just extinguish life, they actively engineer its future.